Well, hey there, kiddos. I hope you're having a really good weekend. We are going to talk about an introduction to slope. We're just going to sort of get introduced to it. What is it? What does it mean? What does it look like? That kind of stuff. Slope is a really important concept, not just in Algebra 1, but in every math class you're going to see from here on out. Slope does not go away. It gets used a lot, and in pretty much every math class I can think of, starting with today, moving on. So slope is pretty important. It's a good thing for you to know. So let's just sort of talk about it. Slope. Slope is the rate of change which compares the change in the dependent variable which is y, and the change in the independent variable. Which is x. So it's just the rate of change that compares the change in the y values and the change in the x values. Positive slope looks something like this when you look at a graph. It could be steeper or less steep, but it looks something like this. And when you have positive slope, the line rises or increases from left to right. It always has to be left to right because that is how we read graphs. We always read graphs from left to right, no matter what language you're reading them in. It's always left to right. Negative slope looks something like this. It could be steeper or shallower, but it is going to be a line that looks very similar to this one. Sorry for my ugly arrows. And with negative slope, the line falls or decreases from left to right. Then there are two other kinds of slope. There is zero slope and there is undefined slope. Zero slope means that I pretty much don't have any change at all. Zero slope is going to look something like this. And y'all are familiar with what this meant when we were talking about distance and speed. It made sense to you. It was you know, we got the horizontal line. It's zero slope. Every time you have a horizontal line, it has zero slope. And we're going to talk about how to remember that in just a minute. But horizontal lines always have zero slope. Undefined slope, which means I cannot define it because it's doing something that cannot be explained, look like this. That's an ugly line. We're going to start over. If it has undefined slope, it looks like this, and the reason its slope is undefined is because it rises and it falls at the same time because it is a vertical line. And I cannot tell whether it's rising or falling, whether it's increasing or decreasing, how fast, how slow. I cannot determine its steepness, which is its rate of change. And so vertical lines have what we call undefined slope. And that's why we use a vertical line when we do a function test, because it has undefined slope, which makes it not a function. And so I use something that isn't a function to see if something is. It's using the converse to prove something, which you're going to learn when you get to geometry, but that's what it is, okay? So just a few other things. Here's how we are going to remember horizontal and vertical lines. We're going to learn these two words, hoy and vux. Hoy, not like in Spanish, it means today. Hoy as in math, and here is what they stand for. In the words hoy, it's an acronym. H means you have a horizontal line. The O stands for zero slope, and the Y means the equation is going to be Y equals. The equation part will be important way later, but you need to understand horizontal lines have zero slope. That's where the hoy comes from. Vux, on the other hand, is how I will remember my vertical lines. V is my vertical line. U means it has undefined slope, and the equation is going to be X equals. And just like I said before, the equation we'll learn that part way later, but you need to remember vertical lines have undefined slope. So if you can remember hoy and vux and have it written down somewhere and actually remember what hoy and vux stand for, it will be very helpful to you. You can also use this lovely, pretty little slope face to help you remember things. It's just a face of lines with different slopes to sort of help you see what's going on. And so you see you have an increasing line, so that has positive slope. You have a decreasing line, which is negative slope, so that's the eyebrows and the eyes. Then vertical lines have undefined slope, so you have this U here for a vertical line. And then horizontal lines have 0 slope. That's why his dimples are the O's. And so it's all lined out for you. This is increasing, which means it has positive slope. This one is decreasing. Y'all should see me, I'm holding my head at a weird little angle to write that sideways like that. Decreasing means we have negative slope. This is a vertical line which has undefined slope, and then of course horizontal lines have 0 slope. So that's the slope face. That's what it's used for. If it's something you want to draw and have available, that's totally fine. It's just another resource for you. So now we're going to use a graph to answer some questions that have to do with slope and rate of change. So we're going to use this pretty graph that's on this page. So we have a graph at the right that shows the average low temperatures in Anchorage, Alaska. The first question says, between which 2 months was the positive rate of change the greatest? So they want it to be positive, so we only want to look at the parts of the graph where it is increasing. The only places it's increasing is from January to July. After July, you notice that the graph starts to decrease. So from January to July, we want to know where the rate of change or the slope was the greatest. So we need to know, where is it the steepest? We're looking for the steepest part of the graph. And if you look at our graph, I believe the steepest part is from here to here. So it's this little section of the graph right here, which is from March to April. So between which 2 months? It will be between March and April. Part B says, between which 2 months did the temperature decrease at the slowest rate? Now I want the decreasing part of the graph, so I'm going to go from July to December, and I want it to decrease at the slowest rate. So I want it to be the shallowest line, the line that is the least steep. And if you look at the sections of the line, the part that is least steep is this piece right here from July to August. So from July to August, the temperature decreased at the slowest rate. And so that's how we use that. That's what we do. We just look at the graph. So now we're going to fill in this table, and we're going to use this table to create a graph and then answer some questions. So we know that Ryan's walking away from a motion detector at 2 feet per second. So I have his speed, 2 feet per second. You have no idea where he started, but you know that he was at the 11-foot mark when the timer called out the 4th second. So after 4 seconds, he'd gone 11 feet. We don't know where he was at time 0 or time 1, 2, or 3, but I do know that he was going 2 feet per second. So what that tells me is that from here to here, I should be adding 2. From here to here, I should be adding 2, and then adding 2, and then adding 2. And so through my table, I should be adding 2 in order to fill it in, because I'm going 2 feet every second. So I'm increasing by 2. But I've got to work backwards through my table because I know only the bottom step. So instead of adding 2, I'm going to subtract. Well, if at 4 seconds he was at 11 feet, that means after 3 seconds he was only at 9 feet. Then after 2 seconds he was at 7 feet, 5, and at 0 seconds he was at 3 feet away. And if you can look and make sure this matches, 3 plus 2 is 5, 5 plus 2 is 7, 7 plus 2 is 9, so my plus 2's work. So my 2 feet per second is being represented in my table. I just walked backwards because I had to go backwards through my table. So we're going to plot some points. Time is going to go down here, and distance is going to go over here. And so we're going to do our time and our distance. So we're going to plot the first one, 0 and 3. At time 0, he was 3 feet away. At time 1, he was 5 feet away. Time 2, he was 7. Time 3, he was 9. And time 4, he was 11 feet away. So there's my graph. And it's a continuous graph because he did not teleport from time 1 to time 2 to time 3. He actually walked all these points And so it is a continuous graph, so we're going to connect the dots, and we're going to draw an arrow because he could have kept walking, but he also could have stopped. So we need to label our variables. I got time and I have distance. We need to know which one is independent. Well, distance depends on time. How far Ryan walked totally depends on how long he was walking. Okay? How long he was walking does not affect his distance. I mean, I guess it can, but in this case, time is not the dependent variable, because time is on the x-axis, and so independent is time, because that's what's graphed on the x-axis. Distance is dependent, because that's what we graphed on the y-axis, and in order to find my distance, I have to know how long Ryan was working. So the next question is, what's the growth rate or the rate of change? Well, we know how fast he was walking. He's walking 2 feet per second. That's my rate of change. So his growth rate is 2. And it's 2 because he is going 2 feet per second. That's how much his distance is changing every second. And then the last question says, how far away from the motion detector did Ryan start? Well, if you look at your table, where he started was time 0 because nothing had happened yet. And at time 0, he was 3 feet away. So there are your answers to that question. Just use the information you have to fill in your table, plot your points, and then independent and dependent after you label. 99% of the time, if you have a time variable, a variable that is measured in some unit of time, that's going to be your independent variable. Very, very infrequently is time going to be dependent. It can be, but it's not very often. So that is introduction to slope. That's what it means. Rate of change. It's going to be a word you hear a lot. I will see you guys on Monday. Have a good rest of your weekend.